trying to understand mechanical systems, they can be overwhelming when you first start to do it. It's usually because mechanical engineers handle this field, and we only really supervise and coordinate with them. But it's good to understand so that we know what implications will affect the design. So stay around and I'll teach you the basic mechanical systems that we deal with on a day-to-day basis. One of the first topics we have to cover when we talk about the psychometric chart is the mechanisms of heat transfer. We have to be aware of radiation, which is the difference between two surfaces. So this is like putting your hand over a pot to check if it's hot or not before you put your burger on. There is convection, which is the one we typically use in design. Hot air rises, cold air sinks. So where you place the air in a building, depending if you're heating and cooling, depends on what temperatures you're looking to get the space and what the room temperature is prior to that. A lot of times this is why we put the intakes lower into the room and the outtakes higher on the ceiling. That way hot air rises out and leaves the building, leaving the cooler air behind when we're trying to cool a space. The other thing is evaporation. We look to this on hot days. When air passes through us, it takes excess moisture off our skin, making us feel cooler. And then there is conduction. This is when we touch something. This mostly happens when we're dealing with the exterior face of a building. You wouldn't put a metal panel at a height that someone can touch it because they could burn themselves. The other thing I would like to mention during this portion of the video is there is this thing called MET. It's dependent on the amount of clothing people are wearing, how many people are in the space, and what activities they're doing. So in the winter, when people are more bundled up to stay warm, that also can change the MET. In summer, it's why you would wear shorts and a t-shirt. When you are doing sports, it's why you want to wear clothes that will keep you cool. And if you ever notice this phenomena with runners in the winter, they will start a race with extra layer of clothing and then they will shed it as they run, as they get warmed up. And the other thing is the amount of people in the room. So if you have a big auditorium, you're going to have a lot more people that are going to be emitting their heat off. That's going to heat up the space. You're going to require more cooling than you might have in a 4 or 5 person office space or room. So those are things you have to think about, as well as how is the space going to be used? What season is it going to be used? How will the people be dressed? And these are all going to determine what kind of heat you have to deal with and what kind of temperatures that people are going to want in the space. So this is the psychometric chart that you use to determine the environment conditions and figure out what needs to be done in order to bring the space into the comfort zone, or what other means and methods you need to do to control the space. This chart looks intimidating at first, but it's not once you break it down into its pieces and start to understand what the different components mean and slowly interpret it piece by piece. That'll be the easiest. So the next step is to go over what each component is. Along the horizontal axis is the dry bulb temperature. This is the temperature of the space just with what a generic thermometer is. It determines how much heat is lost to the air. And a reminder that is heat wave effect. Our bodies are naturally about 98 degrees. Once the temperature is higher than that, our body starts to gain heat from the air, and we actually risk dehydration, overheating, and a bunch of other different health effects. I've actually experienced this on one of my job sites. During a heat wave, I was in a building that was unheated or uncooled on a second floor with no windows. I had to take half-hour breaks in the car every hour and chug about a bottle of water an hour just to maintain a comfortable pace with doing the work, but also staying well hydrated and not overworking. You have to be very careful when we get into those high temperatures. And then to note that, what is the typical average temperature? It's going to be 68 degrees roughly in the winter and 78 degrees in the summer. Also think about the fact that in the winter it's cooler, very, very cold sometimes, especially where I am upstate New York. So here, a 40 degree day can be really, really warm. Whereas in the spring, 40 degree day would feel like it's freezing. And the same thing in the summer, when it's normally 92, that 70 automatically feels cold, even though in the winter it would feel phenomenal. So those effects do interpret how we change and how we feel it. On the vertical axis, we have the humidity ratio, or absolute humidity. This is the actual amount of water in the air. These two come together to form relative humidity, which is the curved lines that you see. This tells you how much water is in the air, and when you hit the dew point, which is 100% relative humidity, condensation forms in the space. You want to be careful of this. You never want water in your buildings unless it's in specific areas. So you have to, this is when you would dehumidify a space. The thing is, if there's too much moisture in the space, your body gets really sweaty and it can't cool off. Again, think of a summer in Florida if you've ever visited there. When you are outside, you might be sweating, but it's too humid to take it off, so you're just constantly sweating. You're constantly trying to dry yourself off to get cool. Then you have the diagonal lines, which are the wet bulb temperature. What this tells you is the difference between the wet bulb and the dry bulb is how much water, how saturated the air is with water. Because once it hits that dew point, it will condensate, as I said before. This is determined by use of sling psychrometer. On this, it's two pieces of a thermometer. One has a wetted tissue that goes over the bulb, and then you sling it in the air until you get the temperature. And then the difference between the two lines determines how much humidity there is. So if the air is really dry, the wet bulb temperature will be a lot lower than the air temperature of the room. When it's high humidity, the two temperatures will be the same. You don't want the two temperatures to be the same. If that is the case, then you have to dehumidify the space. There are also some factors here not shown. Something that we take effect, especially in the summer, is a nice cool breeze. That air velocity and the speed or rate of air going through space can determine how more comfortable a hotter space is. You would experience this in the Southwest, or in like Arizona and Texas. There, you want the cool breeze because it helps keep the... Not there. Any place where you have cooler body temperature or drier environments like the deserty area, having that airflow helps keep the moisture of your sweaty body off of you. So it would feel nice and comfortable to have a bit of air going past you. We don't want too much air though. If you've ever been in a wind tunnel, which really is just any space that acts like a conduit for air and makes it flow at a higher rate. My college had several of these where in the middle of winter you'd be walking and icicles could literally form on the little portions of your eye as they were watering. Then this is also if you live in cooler areas we'll have the wind chill factor. So in the winter, they will give us a temperature saying, hey, the still out temperature is this, but with the wind, it feels like this. So you'll have the temperature that it is outside, and then you will have the temperature it feels like based on the wind rates. And the thing, it's comfortable to have about 20 to 60 feet per minute of airflow. Once you get past 200, it's very, very uncomfortable and unsettling to the human body. So it's something you should be careful about when you're thinking about a space. Most people in interior spaces don't really want to feel the airflow. They just kind of want to feel comfortable in the temperatures that they are in. And you don't want to create a space between two buildings that would influence the wind rate and create a higher velocity of air, because that would make going to the space very uncomfortable. The other thing that we look at is the mean radiant temperature, or the MERT. The best way to explain this is if you've ever sat next to a fireplace or a bonfire, you might have chilly air around you, but that fireplace or bonfire feels beautiful. And that's because of the heat radiating off of the space. You might also feel this in the winter or the summer if you're next to a curtain wall. In the summer, in the curtain wall, the heat comes in, making a space even more uncomfortable. And in the winter, the same place would actually make you feel a little bit more comfortable because it's bringing in that heat similar to the bonfire. And the last thing is enthalpy. And this is about the sensible latent and total heat in a space, and we'll talk this more when we get to the next slides. So as I said with enthalpy, there's a change in heat loads depending on what directions you move through this chart. So if you have more humidity in the air, you're going to have more latent heat. If you have just the temperature go increase, you're going to feel more sensible heat, which just means you feel the heat. You know the temperature is 82, whereas it's going to feel less sensible heat if you're down in cooler temperatures. And then if you have lower moisture, it's going to be less latent heat. And then as you go up, it's going to be more humidity, more latent heat. Then you have the two oddballs is that there's a trade-off. If you both raise the temperature, but you lower the humidity, you're more comfortable in the space, but you haven't actually changed the heat load in the space. The same thing as if you bring the temperature up and then dehumidify the space. It feels more comfortable, but you haven't actually changed the heat and energy. And systems use this to help make mechanical units more efficient. If you can counteract these two, you can use less energy to do the work, which is kind of a cool function. Alright, so basic principles, I think everyone standardly knows this. But the higher the temperature, the hotter it feels. The lower the temperature, the colder it feels. The more water in the air, the wetter it feels, and more humid it feels. And the lower you go in the humidity level, the drier it is. And think about when you're in a drier environment, your lips start to get chapped, your eyes get dry, your mouth gets dry, and you're constantly drinking water. And the opposite, when you're humid, you can't get cool, you feel slimy and sluggish, like there's just ucky feelings in your arms and your hands. So you have to think about these when you're in a space and how do they interact together. So here's something that we understand: the comfort zone and what people enjoy in a space. Then you also can see the zones for climates as well as how we interpret spaces. So hot and humid, cold and humid, cold and dry, hot and dry, dry. Then we can start to use this chart to understand how we can affect the space using mechanical equipment to bring it to the comfort zone. And different zones have different needs. Like in a hot and humid climate, you need to reduce the humidity and you need to cool the space. When you have hot and dry, you actually need to bring the humidity up and cool the space, which might only need to cool the space because the humidity levels will increase as you cool the space. Cold and dry are both times where you need to warm the space and either heat or cool or dehumidify or humidify the space. So if we take these into account, we can start to understand how we can affect the built environment. As we discussed previously, the comfort zone varies between the summer and the winter months. When it's summer, you're acceptable to a little bit more humidity, and you're acceptable to a little bit of a hotter temperature. Ironically, this is showing that humidity is the max humidity is the same, but you can have more variation on the lower limits of humidity. And when we design for this environment, this is typically why we'll have cooling and heating systems or a system that can do both, because the needs in the winter and the summer are different. A lot of schools only provide heating because they're not open in the summer. So you'll have these really weird periods at the end of the school year where it's really hot and they don't have means to really cool the students down. At least that's true where I live. Different areas may be different. This chart, which actually comes from MEB, Mechanical Electrical Systems and Buildings. So it discusses different strategies you can use to change the space to make it more of a thermal comfort level. So if you're way over here, then you can use high thermal mass with night ventilation to cool the space. You can also use evaporative cooling, high mass. Here you want to have gains to get into the zone. So you can kind of see some different strategies to figure out how you can change the zone. And in a broad sense, if you're looking at this chart, as you increase the humidity levels, if you can only provide humidifying only, then you'll get a change in the moisture content of the space, and you'll have a more humid environment. So this is how, if the space is too dry, you would humidify it only because the temperature is fine. And then if you're going in this direction, you know anything up here, you're trying to get water off, more water. In this direction, you're trying to get water off. Here, you're just doing the temperature changes. You're not worried about heat. So your moisture levels are fine. And then here you are all trying to take off and reduce the amount of water in a space. And there's reasons why we do this. So if we know that we have a room that has 80% relative humidity and the temperature is 90, we're going to want to reduce the humidity, and then we're going to want to cool the space. So that's what you'd be doing. If you're coming down this chart, you're going to be doing that drying, and then if you come here, dehumidifying, and as you come here, you're cooling. So it's about understanding what we need in a space so that we can design for that. And then the other advice I give is, for exams, you need to understand how to change a room or a space to make it more comfortable. In the real world, we do get to use mechanical engineers, and they are valuable sources of information. Ask them questions if you have any times you have access to them. They can give you a lot of valuable information that can help you understand mechanical systems a lot better. That's what I used to do for my exams. Every time I focused on one of my exams, I would make a point to try to do some kind of work that was in that area. And when I was doing my exam in this category back in 4.0. I actually worked on a building that was exclusively mechanical, electrical, and plumbing systems with very limited architecture space. And I found that valuable to understand how to use it. So, if you like my video, if you need more understanding and you have a question for me, please comment below, send me an email. I'd love to make a Q&A video answering more specific questions. A lot of this video is just broad scope and overview. So please like, subscribe, send me an email. I would love to help you. And I will see you in the next one.